difference. Difference. It's very important to understand that covalent bonding occurs for things that don't have a lot of electronegativity difference. So if one of them has an electronegativity of 3 and the one next to it has an electronegativity of 2.8, then they're definitely supercovalent. Ionic bonds are the ones that form very far away from each other. I really did work hard on that question to make sure that it wasn't misleading. I understand. Um, you're definitely going to have to forget that I exist whenever you take your praxis. I okay. Well, I really wanted to. I want to eliminate all those things, though. I want it to be where when you think what Dr. Norman said, I want it to be helpful, not not problematic. So I'm gonna. I'll try to change my ways if I can. Um, it probably wasn't just you. Yeah. Okay. Well, thanks for asking that. Is everybody clear about what we just talked about? I mean, if you have any questions about what we just were on about. Yes, I am currently recording. Okay. All right. Atoms and how they interact, right? Everybody through all the videos yet? Yeah, the summary video, because it was boring. Oh, okay. I don't know. I keep editing my videos and I'm like, oh my God, I'm just bored listening to myself. Can't imagine how the students feel. Right. I try not to do that though, because that's like, you know, I don't know. Really, if I had my way, I would super produce these videos. I just don't have time to. I'd like do all kinds of art. Like, ugh, it'd be so much fun. But that's what these are for, so I can draw all the art for you and everything. You can just like draw an S orbital. I'm about to draw you an S orbital. This is what an S orbital looks like. Cool, huh? Oops. I wish I could do this for like it. Yeah. Anyway, plans for the final. um, break it up into 2 sections. It's going to be online, and you'll have basically all of finals week to attempt it. And it's going to be a whole bunch of questions that are kind of sort of praxis like, right? There may be some calculations that you will need to make, but they'll all be multiple choice so that and I'm not gonna hit you with all the, and like I told you, I had an evil professor. I love the guy, but he was an evil professor that would say all of the above or none of the above on every question. And I'm not gonna be that mean to you. So I'll hit you with it occasionally, but not all the time. That way, lots of questions that are supposed to be about um, like the general ideas behind things. So in your quizzes, you've had some. In general, I try to make the first two questions pretty straightforward, and the third question a little bit tough. I'm not sure if you've noticed that pattern, um, but I'm going to try to make this final exam more like the first two questions on all the quizzes, like the easier ones, right? But the ones that are like the real basic, like what do you need to remember like a year from now from this course, right? That kind of stuff. Does that make sense? I'm not sure if that answers your question. Okay, so I had to hold myself back on this set of chapters because there's so much cool stuff in chemistry. Is everybody like clear about what dissolving means? Yes, correct. Or even also in life. Yes. An interesting feature that your book brings up that I don't I don't want you to have to go into very deeply, but like if you take a glass of water, right? And um, so so here's your water, okay, and it's at a certain temperature, right? Um, there's your water. It's at a certain temperature, and you drop salt in there. Let's drop some salt in there. And drop little salt cubes. Um, oh yeah, sorry. Nice. So here's my salt cube. Oops. Here's my salt cubes, right? Dang it. Okay, you get the idea. Some of this is going to dissolve, and it actually depends on the temperature as to how much of it will dissolve. Okay. So what we can do is actually look at what we've learned as to why. So when sodium comes in to this, remember that you have a crystal. Basically, these little salt crystals, they look like this. This is what it means to be a crystal. And we remember, since this is an ionic crystal, I'm bugging everybody with that. Since this is an ionic crystal, it means that simply chlorine has said, give me that electron from the sodium, because remember, sodium is in group 1A and chlorine is in group 7A. And so chlorine has a valency of 7 and sodium has a valency of 1. And they both want either 0 or 8. And so chlorine says, give me that, right? And it becomes negative while this one becomes positive. Everybody remember that? Okay. So this is what our crystal looks like, right? When you put it in the water, then these things start to break apart. That's what it means to dissolve. So you have these little water molecules, like so, right? And when this is introduced into the system, these water molecules are like, well, now we have options. We don't have to be H2O if we don't want to. We can actually split off a little bit. So we can say, let's let then a little bit of this happen. So in fact, it actually, this little hydrogen goes off and starts to connect with chlorines, right? Or it's a much more complicated system than this, and I don't want to. Actually, there's a drawing of it in the book uh, where chlorine kind of joins up to like several oxygen. um, but we're gonna kind of simplify it by look. Uh-oh, I'm I'm here. I'm here. Oh, I see. I think you're not the only one. So okay. Oh, what I was saying is I'm simplifying the system, so this is not exactly technically correct, but it's easier to think about it in this way. Um, the chlorine nabs this hydrogen, right? Because this hydrogen is like it's just a proton. That's all it is, right? Don't forget this oxygen is greedy, just like the chlorine, and so these things are like we're keeping our electrons. I got them, and they're never gonna let go. So this oxygen keeps this electron, right? And this becomes OH negative, right? But this also becomes a proton. So you get, in other words, not an if this were the high concentration in the fluid, you would have a base. If this were the high concentration in the fluid, you'd have an acid. You don't have either one because you have just as many of these as you have of these whenever you put salt in the water. So it's actually neither one. It's not an acid nor a base. It's just water with salt in it, right? But the sodiums, look at this. Look at this. That's a friendly little ion, isn't it? Since the sodium is a positive and it needs something negative to be around, then it's going to go find this thing, while chlorine is going to go find this thing. Does that make sense? That is the process of dissolving. Now, if all of these oxygens, if all of these oxygens are, uh, there's no particular reason that the oxygen would say, I absolutely must be in this state, right? It just is more likely if you raise the temperature. So this one's also pretty happy. If you raise the temperature, there are more of them that separate and are allowed to connect with these sodium and chlorine ions, right? But if you don't raise the temperature, then these little salt crystals are like, man, there's nobody to join with. All of these guys are happy. They don't want to talk to me. Um, it's cold in here. And so they say, I'll tell you what, let's just stay in salt form. This is interesting because what happens is if you have it hot and everything is dissolved and you cool it down, then these here start to form back up with one another because there's just not enough excitement in the water to form these little ions. So this is why you have to heat up your water to get all of the salt to dissolve in it. Does that make sense? I'm hearing either everybody's frozen again or no, it doesn't make sense. Is everybody frozen again? Oh, I didn't scroll down. Oh, okay, okay, good. It's so quiet. Okay. So this is dissolving. When I say, hey, do you understand dissolving? Essentially, it's the idea. This is more specific, but essentially, it's the idea that these things are going to break apart, and they're going to find new partners in the fluid, right? Okay. Different than melting. Dissolving and melting are different things, right? Okay. What else did we go over? It is absolutely the same. Yes, will be the same for all solutions. That when you raise the temperature, you can have more of it in the solution. Correct. And also stirring it helps it dissolve because you're giving it energy. Good. Okay. Other questions about the things that we were looking at in chemistry? Hopefully, I wanted all of this to, like I said before, I wanted this to make sense, and chemistry didn't really make sense to me until I looked at it from a physical, uh, from my field, the standpoint of my field. So that's how I've presented it to you guys, and I don't. This is an experiment, so I don't know whether that's working or not. But I'm open to, you know, questions, comments about how to clarify this better. Okay. What else did we study? I guess I can go look at my summary so that um, if questions pop up, then they'll be visible to everybody. There is there we go. Okay. We had in summary. Um, okay, thanks. Um, Basically, okay, understanding the difference between a physical reaction and a chemical reaction is definitely one of those things that the praxis will demand of you. And also, you know, it's a good thing to be able to teach. Um, my daughter said that when she was in chemistry, her teacher told her if it, you can't reverse it, then it's chemical. I don't necessarily agree with that because the person who said it was a chemist, and so I guess they look at things differently, but there are also irreversible physical processes. But if it helps you to think through it, that was when my daughter said, so if you bake a cake, that's chemical. And it is. It is a chemical reaction. Um, but there are other things that uh, are like if you take um, nitrogen gas and you take a helium gas and you take, in other words, like in the room, right? You just have nitrogen in the room and a helium balloon, and you pop the balloon, then the hydrogen's going to go everywhere in the room, and it's not a chemical process. It's completely a physical process. Why is it a physical process to pop a helium balloon and not and have the helium atoms diffuse all the way throughout the room? It's not a chemical process. Why is that not a chemical process? Well, I was kind of hoping you guys would argue about it a little bit. I know. It's really. Everybody's tired. I'm finally catching up, so I'm feeling kind of energetic. Um, all right, so what did I write here? That's a hint. Oops. Some of us can't write very well, okay, Lori? Nah, I'm just playing. Yeah, okay, see, bonds are broken or formed. So if I release helium from a balloon, I just pop the balloon, helium goes all in the room, then the helium atoms are just wandering around like, yay, we're free now, but there's still helium, right? And then the nitrogen atoms are like, hey, look, a helium atom just went by, but there's still nitrogen atoms. No bonds were broken. I mean, you could argue that when I popped the balloon, that maybe some bonds were broken in the balloon, but the helium escaping is not a chemical process, right? It's a physical process. Now, if instead I released hydrogen from the balloon and then I told you some of the nitrogen formed up with the hydrogens to form ammonia in the room, then you could say, well, now that is a chemical process, right? But I'd have to specify, that that it formed a new chemical by, and you could do that as forming bonds or breaking bonds. Um, so you can, I'm going to see if I can do another uh, demonstration here today um, where I make hydrogen out of water. So that's a chemical process. You would take um, the water and you basically break the hydrogen off and form it into hydrogen gas. And then there's oxygen gas that comes off as well. That's a chemical process. It's also a chemical process to take the hydrogen and the oxygen and put them together, right, to form water. Because I formed a bond or I broke a bond. Does that make sense? I'll take that as a yes. Okay, next. And this is where we were talking about covalent bonding and its importance. Um, yeah, do that. They're really kind of the same idea. Like ionic bonding, covalent bonding, and electronegativity really are all kind of one item, but I just wanted to address them separately. If you have items that are, oh, this isn't available to me. What what did I do? Um, if I have uh, items around this region, or you could have like aluminum and silicon. Those are pretty much just covalent, right? But if you have the ones way over here on the left and the ones way over here on the right, those are the ones that form ions. Ionic bonds. Does that make sense? Okay. Correct. Yeah, they have the same electronegativity here. Um, I actually had to find one that ended on an EM like the other ones, so that it wasn't so obvious. Like, I wasn't trying to mislead though. What was I gonna say? Oh, another thing is that this is a very frequent thing that people have trouble with. Where's my delete all this? The difference between silicon and silicone. Silicon, but nobody ever says silicon unless they're talking about Silicon Valley. Um, most people just say silicon. So silicone is a different thing. And so silicon is the atom on the periodic table. This is an element. Oh, I mean, everybody does. And I've told my kids this is a million times and they still refuse to. So, okay. Not because I mean dad, but because they have all these kids that they're trying to impress. Um, let's look at silicone. That's silicone. It's a very complicated, it's rubber, right? It's a very complicated molecule. So, um, right. Let's look at silicon. That's silicon. It's a semiconductor or semi-metal. Most solar cells are actually made out of silicon. Where am I? Got all this stuff everywhere. Okay. Just a side note. So, okay. What else in this PowerPoint? Um, doo-ba-doo. And y'all know how to. Okay, so let's look at our periodic table here. Ugh, that's so small. Let's look at a bigger periodic table here. And maybe we can just look at this for a while and talk about it. Y'all really should play around a P table. It's a lot of fun. Okay, so if I have a sulfur atom, then tell me, does everybody see where sulfur is? Number 16. Good. Okay, can anybody tell me atoms that sulfur will want to ionically form with? Okay, Lori says column 1. Agree, disagree? Yeah, y'all's. Okay. No? Is everybody even here? That's true. That's true. Alrighty, alright. Let's. Okay, you gotta pipe up though. Agree, disagree? Oh, okay. Thank you, Emily. That's helpful to. Um, okay, so we let's talk through this, okay? Remember that number one goal for these atoms is to have their outer shell filled with electrons, right? In the case of sulfur, it's saying, I really like argon. I want to be like argon. Because argon does have all of its electrons filled in its outer shell. All of these do, right? I want to be just like argon. So it says, where can I find some electrons to be like argon? And how many does it need? Yeah, 1, 2. It is 2 removed away from argon. So if you took argon and you stripped an electron off of it, and then you stripped another electron off of it, you would be at sulfur, at least chemically, like the electrons on the outside, right? Now, that doesn't really happen easily with argon, but, because it's happy. But sulfur, on the other hand, very easily tries to become like argon, right? So it will gain 2 electrons, and it can't just sort of say, I think I will make them, right? It can't do that. So instead, it has to find them from somewhere else. So we go to the other side of the periodic table. Lithium has 1 electron to offer. Sodium has 1 electron to offer. Potassium has 1 electron to offer. Correct, yes. Now it is possible for sulfur to form up with um, with 2 of these over here if each one um, if each one of them offers an electron. But this is a little bit more common for just these can directly offer. Um, and then when we name it, if calcium formed up with sulfur, then we would have. In order to name it, what would we name that? Well, we have a sulfur atom over here, right? And we have a calcium atom over here. And this calcium over here is just looking really super tempting to the sulfur because it has all these extra electrons on it, right? And the sulfur's like, hey, I have spots for those, right? So they join up to form we call them 2 words. First of all, which word comes first? Lots of stuff here. Let's Oh, I got a bleep. Who's that? Okay, so let's. I didn't really get into this, but here's a good time to talk about this. 8 generally means that it ate oxygen. Okay. Um, uh, so let's look at. Where's my other. Oh, here we go. Okay. So we'll look at sulfate. Do you see what sulfate looks like? Can everybody see that? It ate oxygen. Okay. So we don't have any oxygen here. So we're not going to end up with an 8. There's no oxygen to eat. All right. Let's go with the first rule. You always read left to right. So that the atom that is farthest left on the periodic table comes first. Right. So we're going to put calcium here. We'll correct these as we go. Calcium here and sulfur here, right? Now then we have to think about that. All right, what is the mono, di, tri, blah, blah, blah? First of all, first of all, first of all, this is an ion, right? An ionic bond. And with ionic, you don't have to specify di, tri, or any of that. Right, exactly. So it's important first for us to remember that this is an ionic bond, right? And if it's an ionic bond, then that means we there. Why do you think it is? Let me ask you. Why do you think it is that we don't have to specify whether it's di or tri or any of that with ionic compounds? They steal electrons, yes. No, no, no. I mean, it's true. That's a good point, and it's definitely related to what we're talking about. I just want to make sure that it's absolutely clear to everybody why that matters. With an ionic compound, um, you're not going to have, um, like I said, you're not going to have like sulfur go over here and be like, I think I'll form up with a couple of these guys, right? It just doesn't want to do that. It wants one atom that it generally tries to have one atom that it can form up with. Now, there are some times when you have like magnesium, uh, you can have magnesium oxide, you can have magnesium fluoride, you can have that. But I don't have to tell you, if I say magnesium oxide, I don't have to tell you how many there are. I don't have to say that this is magnesium monoxide. I don't have to say that because magnesium gives 2 electrons and oxygen takes 2 electrons. And it just makes sense then that as long as one of them satisfies one of them, then there should be one magnesium and one oxygen. When I say magnesium fluoride, then you can say, oh, you don't have to tell me that that is dimagnesium fluoride. You can just say magnesium difluoride. You can just say magnesium fluoride. Why can I just say that? Because I know that magnesium has 2 electrons to offer and that each fluorine steals one of those electrons. So that means I need 2 fluorines to satisfy one magnesium. Okay. And so that is why it is absolutely unnecessary for us to claim whether this is mono or di or tri when it comes to ions, because it's immediately mathematically determined for us. But by convention, we do take the end of our second word and put "ide" on there. Yes. Yes. I don't know if that's actually a compound that readily forms, but probably you can form it. It probably doesn't form as easily as some other things do. But Yeah, I'm gonna keep it simple in you go left to right with ions, and with covalence, you go left bottom to right top. So it's pretty much the same. But you can kind of see the trend here, can't you? Where this little diagonal line is, you're going to go from left and then up like that with covalent compounds like that. But um, if you were to form like gallium and tin together, then that might be a little bit like that would be mean of me to put like what do you call that, right? Like, so I'm not gonna do that to you. Um, the correct answer is you're a meanie. Okay, so but if I did give you germanium and phosphorus, then you could say, oh yeah, I know which one goes first. Germanium goes first and phosphorus goes second. Does that make sense? Okay. Now, with these covalent compounds, boy, they do, you have to, they're all kind of mixed up. So you really do have to specify. Um, like if I say iron oxide, for instance, iron oxide is, well, it's actually a metallic bond, but that's okay. Anyway, it's kind of, yeah, it's partially covalent. So if we do iron oxide, I haven't, but this is a really great example of if I have iron oxide, I can have uh, um, this. I could be saying this, or I could be saying this. Well, that's not very helpful, is it? So I have to claim, I would then, if I wanted to write this out, then I would have to say iron. Now, you don't need to know why this is. I'm just letting you know that we have to specify. One of them is this, and the other one is this. For reasons that we won't go into. This is a state, okay? And so, like, we have to be able to specify which one we're talking about. The new form of, um, you'd be glad you don't have to learn the old one. That's why I hated chemistry so much, that I couldn't remember all the words. They would, ferrous, ferrous oxide or oxide of ferrous, or, and they'd be like, what, ferric oxide. We're like, good God, guys, come on. Y'all got come up with a better system. Well, they did. They came up with a better system where they say iron 2 oxide or iron 3 oxide, and that tells you what state it is, right? Now, you do not need to know iron oxide. It is cool to know that it's rust, and it's actually in one of the videos too. It makes a cameo in one of our videos. But it's a little hard to figure out the chemistry of, so we're kind of sticking with the easy ones for now, okay? But I mean, the idea here is, and I think in my video, one of the things that I bring up is uh, you have carbon dioxide and carbon monoxide, right? Okay. Uh, Carbon dioxide is still poisonous to us in large quantities, but obviously it's not poisonous to us in small quantities because we're constantly breathing it out. So, the only issue with carbon dioxide is don't get too much of it because then your lungs can't actually eject it and it backs up in the blood. But carbon monoxide, on the other hand, well, that's a real problem. And so, um, how do you know if you say carbon and oxygen, and then I tell you, hey, I have this, let's get rid of all this stuff since we have our answer now. If I say carbon and I want 2 oxygens, so then if you want to write that out, you have to actually specify what that is. If I asked you, hey, I have a molecule that's made out of carbon and oxygen, then you'd say, well, those are next to each other, so that's a covalent bond. And I would say, okay, I don't know how many oxygens you have, so I need you to be more specific, right? Well, I wrote it down for you. Now I'm more specific. I have two oxygens for every carbon atom. Oh, okay, okay. Well, that would be then, if I wanted to write that out, carbon is to the left, so I'll write that first. And then I have oxide, but I need to tell you how many of them. So it's not monooxide, it's dioxide. Does that make sense? And also, you never have to do this. You never have to tell people that that's monocarbon, right? The first one is always going to be assumed to be one unless otherwise stated. You could, what about this one? Technically, yeah, what's technically, we call this something in everyday life, and the old chemical system, it has a name, um, but mhm, similar to water, but don't drink it. So this, no, no, but it does, it's not chlorine bleach, but it will bleach some things. So it's actually rocket fuel. But it's yeah, but it's also commonly known as hydrogen peroxide, right? One hydrogen for every oxygen. But in our chemical system, we would label this. Well, we have hydrogen is to the left, and oxide for the right. And this time we have dioxide, but since we don't have one, remember, we don't have to write anything if there's one, but there's not one, there's two. So we need to write dihydrogen dioxide. And that sounds stupid and nobody ever says it. They just say hydrogen peroxide. But this would not be incorrect. People would just look at you weird if you said it. And then I think that they also mention in your book another one that people never say, which is dihydrogen monoxide, right? Did you guys see the big thing that went around about dihydrogen monoxide? This is really great and a good thing to show your students. Dihydrogen monoxide. I'm getting some people talking over here, so I want to see what they're saying. There's a whole website that's the hydrogen monoxide research division, and they give you all this like dangerous stuff. Like hydric acid, uh, disruptive cell membranes, uh, chemically alter critical neurotransmitters, um, atomic components of it are found in a number of caustic, explosive, and poisonous compounds. In other words, hydrogen and oxygen are found in those things. Um, it's they have all this stuff like it's in most of the stuff in your home. In gaseous form, it causes burns. Like there's all this just super scary stuff about this chemical compound that's like invading everyone's homes called dihydrogen monoxide. And all that stuff is true because in gaseous form, it certainly does burn you. I've been burned by steam several times, right? Um, so they put things in there withdrawal from it's so addictive that withdrawal from it means certain death, right? Well, yeah, I mean, if you don't if you don't drink water, you're gonna die. So it's really a wonderful uh, sort of introduction to kids about misinformation. But understanding your chemical compounds, you can look at something like that and go, "What? No, uh-uh." Okay. Um, let's see what else we've got on here. I just want to make sure I'm clearing up anything that's confusing to people. Do-do-do. Sh- sharing electrons. That was maybe a little bit confusing on the colors, but I didn't know a better way to do that. Um, this one's not too bad, is it? Avogadro's number. Is everybody okay with the idea of a mole? I don't know if I can hear everybody. Are you guys frozen again? Oh, okay. I see. Okay. Now, well, the way I introduced this originally was as a Ralph. Remember that? Like, if you have a billion atoms, then we could just call it a Ralph. And then we know that if you have um, one Ralph of carbon dioxide, well, then that means that you have a billion carbon and 2 billion oxygen atoms all formed together into a billion carbon dioxide molecules. And so you have a Ralph of carbon dioxide. If you were to separate it into individual atoms, you would have one Ralph of carbon and two Ralphs of oxygen. Does that make sense? This is the same concept, except for it's just a weirder number than the number 1 billion. It's a number of uh, like 602. No, what do I write that? Should be 600,000 million million million. Okay. Uh, it's really hard to fathom. It's so many. So, but that's like if you hold if you take a tablespoon, well, it's probably more than a tablespoon. It's probably more like a quarter cup or something like that of um, of like charcoal, then and throw it in uh, in a bucket. Then you maybe that's somewhere around a cup or something like that of charcoal. That's like a mole of carbon, right? A mole of air is much bigger because it's not very dense, right? But I mean, this is everyday volumes. In our room we have in a room right now you're breathing in. There's some couple of moles of air, right? Several moles of air. And then if you're drinking coffee, then you have, like somewhere around a mole of coffee that you're drinking. So this is why we use this, right? Because it actually is how many atoms, but it's put in terms of everyday things like grams. Does that make sense? And if we look at our periodic table, let's go back to our periodic table. We have um, let's say aluminum. Aluminum's fine. Uh, this gives us the um, the average weight of aluminum, so including all of its different isotopes and everything. Which is fine, because what that means is that if we take aluminum and it's just sort of like all of its, cousins, right? All of its isotopes. If we take aluminum and I hand you exactly 1 mole of aluminum, guess what the weight of that is? I don't know if you can see it on here. Yes, it is 26.982 grams. If I hand you exactly 1 mole of aluminum, I have handed you 26.982 grams of aluminum. 1 mole of aluminum, then I've handed you 26.982 grams of aluminum. This is where the definition of mole came from. Does that make sense? Um, so it's just a convenient way to, instead of 1 atom, 2 atoms, we're like 1 mole of atoms, 2 moles of atoms. And the ratios then stay the same on these different molecules, right? If you have carbon dioxide gas, you're always going to have twice as many oxygens in there as you have carbons, right? Unless, of course, you accidentally form some carbon monoxide in there. But if you manage to make sure that it was all carbon dioxide, then you know that that ratio is the same, and so the molar ratio would also be the same. Okay? All right, go back to so we're not going to actually run calculations on this. I just want you to be able to, in the future, if you want to do calculations, you would understand the basis behind it. I don't think there's anything to calculate in this particular, because I remember thinking when I went through the summary, I was like, I don't have any real equations to offer them. So it's all just I mean, it's really just pluses and minuses, right? It's just taking away, electrons and adding electrons is essentially the entirety of chemistry can be uh, boiled down to the simple principle of, hey, where do electrons go? And that's it, right? I mean, obviously, it gets much more complicated than that simple sentence, but it's also always going to be related to that simple sentence. So it really isn't necessary for us to go into the math of it all in order for you to understand the basics. Acids, remember I said here that it releases hydrogen proton donors in the video, and if you have an oxygen atom here, then these are sort of, they're not really, I don't want to put positives on there because they're not ions, right? They're actually sharing electrons with this oxygen. But you got this hydrogen proton that's like in the neighborhood, like the new kid, right? Comes along and says, "Hey, would, you know, I would like to join into this in this it's somewhat stable. So you end up with basically 3 hydrogens and an oxygen, and they form this sort of like odd little sharing covalent system, right? It's entirely going to be net positive by 1 because this hydrogen came in with 1 extra proton but no extra electrons, and so this will be net positive, and that's the hydronium ion. And so really, in your mind, you don't have to think about this. When you read about hydronium, you can just talk about it like, oh, that's basically talking about protons wandering around in a solution. So it's either one, right? Because I mean, this right here tells you that it's net positive by 1, and it's only due to the fact that there's an extra hydrogen proton running around. So you might as well just think of it as a proton. pH scale's not too bad, is it? Solvents, just remembering the difference between a solvent, solute, and a solution, right? I put here salts. Yeah, actually salts are what tends to form. If you take an acid and a base, if you were to take like a solution that has a pH of 5 and a solution that has a pH of 9, those are both removed from a neutral solution by 2. One of them in the acidic direction and one of them in the basic direction. And if you joined them together in equal quantities, then to make sure that their concentrations, the concentration of what causes this to be 5 and the concentration of what causes this to be 9, if you put those together, you'll get a neutral solution and salt. Not table salt, but a different kind of salt. Any of the ionic compounds that we talk about, like magnesium oxide, are considered salts. So you're going to get, in other words, an ionic solution, just like your, very similarly to your table salt solution. If you join an acid and a base, they neutralize and then they send all these like little salt ions into the solution. So different kinds of salts, not necessarily sodium. So, but this is what makes it conductive. I don't know if anybody saw the demonstration that I posted. No? Did anybody see the demonstration I posted with the conductivity? Oh, yes. That is basically that is the definition of electrolyte. Anything I put in there that causes that to conduct would have to be electrolytes. Water is extremely insulating by itself, but like if you put electrolytes in there, it becomes conductive. Now, most of this stuff that comes out of your faucet is automatically conductive because not only does it have like treatment in there, like fluoride treatment, but it also has like minerals all in it, right? So, it's not pure water that comes out of your faucet, or groundwater is not pure water. It's got lots of minerals in it. I had to go to the store and buy pure water. So, um, I yeah. It's like, oh my gosh, that poor person. No, that um, I could have, but I could have poured apple juice in there, right? And it would have worked right. Or salt water. Um, and you can make fruit clocks based on this principle, right? If you have the electrodes, the correct electrodes, I think you buy these at the store, or you can just make them. Um, and you can just put you can take copper and zinc, and you can just poke them down into a fruit, and then connect them to a clock, and the fruit will power the clock because it's basically a battery. It's basically just got all of these ions that are like, oh, look, copper, and they'll move one way, and then the other ones will be like, oh, look, zinc, and they'll move the other way, and you've got a current. So this is the concept behind electrolytes. Electrolytes are basically just things that conduct in a solution. Okay. think that's pretty much everything. What did I do down here? What is this? Oh, okay. That's the process of conducting. Okay. Anyway, other questions? Anything? Chemistry makes. Let me double check to see if anybody's been sending comments on here. Oh, okay. Are they? They're supposed to be serious. No, I started this after it started to, like because we went into quarantine, and I was like, well, I got to get my demonstration somehow, so I started doing that, and I guess a lot of people like science. I guess that's good, but anyway, so I have to keep coming up with more. So I'm probably going to come up with another one where I uh, um, create hydrogen out of water, and you guys can see that process. It's easy. You just need a 9-volt battery. Okay. Other questions? Well, you don't have to ask them now. I mean, if you think of questions, you can always email me. And then also, um, today I'm gonna send out instructions, or not instructions, but I'm gonna send out a reminder to everybody in the class. Tomorrow I will be providing your exam, your your third exam. Yeah, your third unit exam. And then you can work on it and whatever format helps you do it digitally on your computer. You can print it out if you need to, and then submit it to me by Wednesday. Yes, you have to submit a PDF to me by Wednesday, and I'll send you instructions tomorrow about how to do that easily. So it'll be nice to be able to sit down at your own pace at a table or whatever and work on it. So hopefully, hey, that's my y'all. Okay, okay. Um, Welp, keep up the questions, guys. I want to make sure everybody does super well on this, okay? So, email me if you've got anything. Um, you quiz, uh, you got one more quiz tonight, and then I'll have another quiz put together for you next week. That's the super quiz, gives you kind of the chance to get back some points. Okay? Okay. Oh, it did. Tomorrow's Friday, isn't it? I'll have to talk with Mr. Jean about this, and we'll make sure that you have a good. Are you having lab though, Mr. Jean? You having lab tomorrow? Okay, I'll talk to him about it and see. Yeah. Okay, y'all take care. Okay.